Today we will discuss about fits and tolerances. Being an engineer, I'm sure you understand the benefits of using fits and tolerances in technical drawings. Let's get started. Tolerance dimensioning. Tolerance is the total amount that a specific dimension is permitted to vary. It is the difference between the maximum and the minimum limits for the dimension. For example, a dimension given as 1.625 plus minus 0.002 means that the manufactured part may be 1.627 or 1.623 or anywhere between these limit dimensions. In the figure, you can find that the shaft is of 1.248 and 1.247. That means the tolerance in the shaft is 0.001. So as in the hole, the tolerance is 0.001. Now we will talk about allowance and clearance. Here we have three different figures, A, B and C. Now we have shaft tolerance 1.248, that's the largest shaft, minus 1.247, that's smallest shaft. So we have tolerance of 0.001 and hole tolerance is 1.251 minus 1.250, so tolerance is 0.001. Now loosest fit, that means we will use the smallest shaft, that 1.247, and the largest hole, that is 1.251, and in the tightest fit we will have largest shaft, that is 1.248, and smallest hole, that is 1.250. So the allowance will be 1.250, that's the smallest hole, and 1.248, that's the largest shaft, right? So that will be the allowance, and the maximum clearance in these situations will be 1.251, that is the largest hole, minus 1.247, that's the smallest shaft. So 1.251 minus 1.247 equals to 0.004. That will be the maximum clearance. Now let's talk about size designations. So what is nominal size? It is the designation used for general identifications and is usually expressed in common fractions. For example, in the previous figure, the nominal size of both hole and shaft, which is 11/4, would be 1.25 in a decimal system of dimensioning. Basic size or basic dimension. It is the theoretical size from which limits of size are divided by the applications of allowances and tolerances. Actual size is the measured size of the finished part. Allowance is the minimum clearance space or maximum interference, obviously, intended between the maximum material conditions of mating parts. You can go back to the previous figure and you can understand the designations clearly. Fit between mating parts. Fit is the general term used to signify the range of tightness or looseness that may result from the applications of a specific combinations of allowance and tolerances in mating parts. There are four types of fits in mating parts: clearance fit, interference fit, transition fit, and line fit. So what is clearance fit? An internal member fits in an external member as a shaft in a hole and always leave a space or clearance between the parts. Minimum air space is 0.002. This is the allowance and is always positive in clearance fit. Right? So 1.250 minus 1.248, that's 0.002. Interference fit. The internal member is larger than the external member, such that there is always an actual interference of material. The smallest shaft is 1.2513 and the largest hole is 1.2506, so that there is an actual interference of metal amounting to at least 0.0007. So you can find in the figure. Under maximum material conditions, the interference would be 0.0019. This interference is the allowance, and in an interference fit it is always negative. Transition fit may result in either a clearance or interference condition. In the figure below, the smallest shaft, that is 1.2503, will fit in the largest hole, that is 1.2506, with 0.003 to spare. But the largest shaft, that is 1.2509, will have to be forced into the smallest hole, 1.2500, with an interference of metal of 0.009. Line fit. The limits of size are so specified that a clearance or surface contact may result when mating parts are assembled. Now let's talk about basic hole system. Minimum hole is taken as the basic size. So minimum hole is taken as the basic size. An allowance is assigned and tolerances are applied on both sides of and away from this allowance. So here minimum clearance will be 0.500 minus 0.498 equals to 0.002, and the maximum clearance will be 0.502 minus 0.495 equals to 0.007. The basic size of the hole, 0.500, is taken as the basic size, right? So this is taken as a basic size. An allowance of 0.002 is decided on and subtracted from the basic hole size, making the maximum shaft as 0.498. Tolerances of 0.002 and 0.003 respectively are applied to the hole and shaft to obtain the maximum hole of 0.502 and the minimum shaft of 0.495. Moving down to basic SAP system, maximum SAP is taken as the basic size. Here, an allowance is assigned and the tolerances are applied on both sides of and away from this allowance. So here minimum clearance will be 0.502 minus 0.500 equals to 0.002, and the maximum clearance will be 0.505 minus 0.499 equals to 0.006. So the maximum size of the SAP, that is 0.500, is taken as the basic size. An allowance of 0.002 is decided on and added to the basic SAP size, making the minimum whole as 0.502. Tolerances of 0.003 and 0.001 respectively are applied to the whole and SAP to obtain the maximum whole of 0.505 and the minimum SAP of 0.499. Now, the specification of tolerances. So how do we specify the tolerances in the dimensioning system? So here we have different examples of like limit dimensioning. Here you can see we have the higher limit is placed above the lower limit, as you can see in the SAP and the whole. So this is the limit dimensioning. And in the next example, where we have single line note form, the low limit preceding the high limit separated by a dash. Moving to next specifications. So now we have plus or minus dimensioning. Here we have two different types: unilateral tolerances and bilateral tolerances. You can find the formations of tolerances in the dimensioning system, right? So you have unilateral tolerances in metric system as well. So you can find the examples, and you can find the bilateral tolerances here and again here, right? So in the technical drawing, we will use this kind of plus or minus dimensioning to define different tolerances. Now the cumulative tolerances. Here we have two more examples where we have cumulative tolerances. So as you can see, we have the cumulative tolerances technique, and in the right hand side we have baseline dimensioning, that is also cumulative tolerances. Right? So you can see the example. So this is the workpiece and these are the dimensions. Right? Now tolerances related to machining process. Tolerances related to the machining process. You have a list of tolerances and the machining process, right? So you can take reference the standard tolerances from the list. Now you have different terms related to metric limits and feet, right? So we will go next one by one and explain each of the terms, like maximum size, minimum size, fundamental deviations, upper deviations, lower deviations, international tolerance grade, we will discuss later on, basic size, lower deviations, upper deviations, and fundamental deviations, minimum, maximum, for both SAP and whole, international tolerance grade. So here are the different definitions, like basic size is the size from which limit or deviations are assigned Basic size, usually diameter, should be selected from a table of preferred sizes. Deviations is the difference between the basic size and the hole or shaft size. Upper deviation is the difference between the basic size and the permitted maximum size of the part. Lower deviation is the difference between the basic size and the minimum permitted size of the part. Fundamental deviation is the deviation closest to the basic size. Tolerance is the difference between the permitted minimum and maximum sizes of a part. You can always go back to the previous screen to understand the definitions properly. So here is the international tolerance grade formations. As you can see, 50H8 and 50F7, 50H8F7. So to decode, you can see the decode information. So in the fundamental tolerance grade, you can have a tolerance and you can grade and you can decode as we are seeing on the screen. There are a set of tolerances that varies according to the basic size and provides a uniform level of accuracy within the grade. Here we have a few of the more examples that you can decode. So more definitions now. We have tolerance zone, refers to the relationship of the tolerance to basic size. It is established by combinations of the fundamental deviation indicated by a letter and the IT grade number in the dimension 50H8 for the close running fit. The H8 specifies the tolerance zone. The whole basis system of preferred fits is a system in which the basic diameter is the minimum size. For the generally preferred whole basis system, the fundamental deviation is specified by the uppercase letter H. The shaft basis system of preferred fits is a system in which the basic diameter is the maximum size of the shaft. The fundamental deviation is given by the lowercase letter h. An interference fit results in an interference between two mating parts under all tolerance conditions. A transition fit results in either a clearance or an interference conditions between two assembled parts. Tolerance symbols are used to specify the tolerance and fits from mating parts. For the whole basis system, the 50 indicates the diameter in millimeters. The fundamental deviations for the whole is indicated by the capital letter H, and for the shaft it is indicated by the lowercase letter f. The number following the letters indicates that IT grade. Note that the symbols for the hole and shaft are separated by the slash. Tolerance symbols for a 50 mm diameter hole may be given in several acceptable forms. The values in parentheses for reference only and may be omitted. Here we have few more examples for your reference.